Let me start over. I was muted. Welcome back, folks. Well, it's time to get started. Looks like it'll be kind of a small class today, but we'll still definitely get through it. I'm glad there's at least a representative in class and in Zoom as well. Before we get started today, any questions at all? Okay, well, today we're pretty much just finishing up the course content. We're on the last part of the last example of the chi-squared procedure for two-way tables. Then we're going to look into the one-way ANOVA procedure, which is pretty in line and similar to what we've been doing all along in chapters 21, 22. It's going to be an extension of what we did in chapter 18 when there's two sample means. Now we're considering three sample means, or four or greater. Whichever problem we end up on, we'll finish up when we go into the review week, and that will be considered the entirety of the course content. Our final exam is going to be comprehensive. It won't involve every single problem that we've discussed because then it's too long, even as a take-home final exam. So I'm not going to write a gigantic packet of work for you to do. What I'll be doing is selecting a sample of methods from here. Maybe not every single method, but a good quantity, good proportion of them. I'm going to randomize the problems, and then it's going to be kind of like a homework assignment. You'll be asked to do complete analyses on the various scenarios, and you can use this document here to guide the analysis. What we'll be doing is pretty much the same. We're going to do a essentially take-home final exam dress rehearsal for our review week. I'm going to make a new review set of problems where all the questions are randomized, and we'll do the hard work of deciding what procedure from here is going to fit into our data. So you'll have a good idea of what the real final exam is going to look like before we're releasing it, because we're going to be, for our review, essentially just doing a different version in a real sense. So that's our goal for today and the entirety of next week. On Wednesday, the last 15 minutes of our review will turn over to just going into Canvas, unlocking the final exam so that you can now view it at that point, download it, start working on it, and we'll just have a short discussion about the exam as a class. Well, pretty much that's what's on the menu for the last part of the course. The final exam will be due Thursday on finals week, but if you want to work on it early, get it done as soon as possible, you're absolutely welcome to hand it in early as well. Any last questions or comments at all, folks, before we get started? Okay, well, let's jump in. We're about to finish off our work in the chi-square test for two-way tables. Really, chapter 22, chapter 21, our author could have put both of those chapters together if he really wanted to. They're both pretty short chapters, but it's kind of nice that they were kept separately because one of the things our author is trying to do is separate every single chapter according to particular statistical methods, which are chosen purely based off of what variables we're dealing with. So once again, just for the reminder, in chapter 22, the only reason we're doing the chi-squared for two-way tables is because we have exactly two categorical variables, as well as one of them at least has three or more outcomes. So that's what was going on in this particular problem. It's kind of interesting data. We were looking into the relationship between incidence of CHD, coronary heart disease, as well as baseline trait anger, not the same as situational anger, having a bad day, just more of a personality trait. The null hypothesis was no relationship between coronary heart disease and trait anger. Here we're just talking to them about them as variables. We already said what the outcomes are for each one of those variables right above. The alternative hypothesis insists that there is some relationship, and we tested it at the 5% significance level. In fact, we pretty much nearly complete these data. All it's missing is the conclusion. But let's recall what we did next. We import the data into RStudio, which was allowing us to find the expected counts. This allows us to check the conditions. And then it gave us the chi-square test statistic and the p-value. We found that it was highly, highly significant. The syntax is on these notes, but let's also pull it up here in RStudio. So I've shared this for both problems, and it's highly adaptable to a homework question for the chapter 22 homework, and highly adaptable as well for, say, if you find the chi-square two-way table problem on a final exam. All you have to do is change out the data. If there's 3 rows, just change the row to 3. Then change the names here according to what your categorical variable outcomes are, and the rest of the syntax runs. This last line is optional, but it's kind of informative if we do reject the null hypothesis. It tells us the critical reason of why. So when we ran this, it outputted the expected counts table. After we had the expected counts table, we can also run it again and get the chi-square components. So if we look into the chi-square components, the expected counts, and the original counts from the data right at the top, let me try to scroll to the right spot here, give me a moment. There's a lot of things to connect all at once. We're connecting this information together with the actual real data that the problem found, together with the chi-square components themselves. So we know the data is highly significant, which means we're rejecting the null hypothesis, which means our conclusion is that there is some relationship between these variables. They are dependent, not independent, in other words. But that's where our test ends. Our entire book only really gives the overall test. And if you want to say a few more words about this kind of problem, you'd have the opportunity to do so if you looked into the chi-square components. So here's the thoughts that we connect together. If we were doing a follow-up analysis, more procedures, possibly another confidence interval to go along with these data, we would first take a look at which chi-square component is the very largest in these data. It's this one. It's for coronary heart disease intersecting with high anger, high trait anger. So that right there is the reason our p-value is minuscule, why the test statistic came out gigantic. Low anger also mysteriously had a big component there, but it was really majorly all due to that one cell. That tells us what the relationship is between our two variables. Next, if we look at our expected counts, these are the counts we would expect to see if we fail to reject the null hypothesis. If the null hypothesis is actually exactly true for our data for these variables, these are the counts that we should have gotten for the sample size of the study. And if we look across these expected counts, notice how not so different they are. It was from 53 to 69. That one was a slight difference. So a slight bump on that chi-square component. But the rest of them are very close. The relative error between them is small. 3,040 expected, 3,057 is what we got. For moderate anger, even closer, 110 is the real data. What we found is about 106 and so on. But if we go from, say, that cell, if the null hypothesis is true, we should have been getting around 14 expected counts. But we got almost double. The relative error is gigantic in that one tiny cell there. In high anger, there was a huge amount of coronary heart disease events in our data. That's why the chi-square test statistic is so large and why we're rejecting the data. It looks like there is a relationship between coronary heart disease and incidence, or excuse me, there's a relationship between coronary heart disease and trait anger in the sense that high anger seems to correlate with coronary heart disease. But notice one thing we can never say is high trait anger caused the coronary heart disease. That would be a conclusion we cannot make because this was not an experimental design. So once again, we're going to make kind of an overall test conclusion, but if you're interested in saying a little bit more about it, these values right here is what guides the results. So coming down below, here's where we're going to now finalize the problem. But any questions or comments at all, folks, with the recap or follow-up discussion on this one? Okay, well, in the end of the day, it's another hypothesis test. A significant p-value like that means the first thing we want to say is we found significant statistical evidence in favor of this outcome. So if you left your conclusion right at that stage, that would be appropriate for any homework assignment, any take-home exam, for an example. Anything you say for follow-up words is just extra, but make sure you target specifically that you found evidence for whatever that alternative happened to be. So let's write this in by saying, this study provides significant statistical evidence and this is at the, I forget, 5%, it says down below there for alpha, at the 5% significance level, of, then we go to our alternative hypothesis, which says there is some relationship between coronary heart disease and trait Anger. So let's say of some relationship, I'll say it in these words, incidence of coronary heart disease and the trait Anger had low, moderate, and high trait Anger, but we can abbreviate that if you choose and say, and the levels of trait Anger. And if you want to be specific, just say low, moderate, and high. But if you say just levels like this and paraphrase a little bit, I would say that's not harmful at all for this kind of problem. And again, that's where our book work pretty much ends. Our textbook doesn't go into the follow-up test. Our follow-up test would look into the chi-square components to analyze which of them are significant, say that one and potentially that one out of 4. And then we can define parameters. There's really 6 in total. But one parameter right here of great interest would be the true proportion of all individuals having high trait Anger that eventually get coronary heart disease in 4 years. We can put a confidence interval on that, but then that's more statistics. It goes beyond our textbook. So once again, for our class, just doing the overall test, this is an appropriate spot to end at. So we'll end the problem here. Below is the syntax that did the complete analysis. The chi-squared components, we said not required, but it's interesting if you reject the null hypothesis to see exactly why. But any last questions or thoughts, folks, on the wrap up for this analysis? Okay, well, again, congratulations. We've gotten through the analysis. And I want to say just a little bit more because these tests, again, are pretty weird. This is an overall test trying to look for any kind of relationship. And it's not too different from when we were, say, in chapter 18. We did a statistical analysis for a hypothesis test. Let's find one. This was a controversial data. And here we said we have significant statistical evidence that the mean TAT score for mothers of normal children and schizophrenic children are different. And then we just stopped because that's the overall test in the problem. If we want to go beyond, we would look into the hypothesis. We found evidence of that, but we want to say what is the nature of the difference, put a confidence interval on mu1 minus mu2. And that's the kind of situation we're here in with this data in particular. We ended on the overall test, but if we want to go further, we could do more statistics on this one. And I mention all that because if you ever have to do a chi-squared procedure and you found it significant, it's good to know that we go beyond what our introductory textbook did on this problem. But now for our last chapter, what we're going to do, because we've took a lot of time looking into categorical data after taking a break for quantitative data, we're going to return to quantitative data, like in these problems here. This was our chapter 8 problems. And in chapter 8, let's see, let me scroll to a good spot. This is what the methods look like. This is the confidence interval procedure. This was the test statistic. We never made an assumption of equal variances, so we never used a pooled variance statistics whatsoever. And our null hypothesis was that a difference is zero. Our alternative hypothesis is that their difference is either not zero, greater than, or less than. Now, what we're doing is extending this. We want to say, what if there are three parameters, mu1, mu2? Note that if you say mu1 minus mu2 is zero, it's the same thing as saying mu1 equals mu2. But that would mean you have more than two samples, more than two independent populations. And that's what this procedure is all about. The chapter 24 one-way ANOVA procedure says you have one quantitative variable. So some quantitative variable together with a categorical variable. The role of this variable is to say what are the independent populations from which our samples are going to come from. And this time we have at least three. That says chapter 18, the one we were just looking at, is off the menu. This only works for exactly two outcomes. So all we're doing is extending our work in chapter 18. If we extend in chapter 18, here's what the procedure is going to look like. First, we're doing a pretty wildly different procedure. We're not going to use a chi-squared probability distribution. We're not going to use the normal distribution nor the t-distribution. In this one, because we're analyzing variances, whenever you are doing some kind of variance work, you're often dealing with the so-called F probability distribution. So new probability model, and in our statistical class, any probability model that occurs is because the test statistic follows that probability model. This one's complicated. It's a ratio of chi-squared variables. So it is not one chi-squared altogether, but rather a ratio. It'll have degrees of freedom in the numerator, m, degrees of freedom in the denominator, n. And our job is not necessarily to memorize these formulas. These are just here for the mathematically curious. How would you define this probability curve? Another really, really complicated distribution. And this is a theme ever since the t-distribution. All of these, from the t-distribution, from chi-squared, now to the f-distribution, had something to do with the gamma function defined down below there. If we were to get a good visual of what this even looks like, it's similar to chi-squared in that these are often violently skewed to the right. So this is what an f-distribution would look like. If the numerator degrees of freedom is 3, that would tell us our categorical variable has 4 outcomes, because then the degrees of freedom is 1 less, a 3. The denominator degrees of freedom is going to be the total sample size minus the number of outcomes. That would be a 4 in this. So we get a right skewed shape for this situation. Change n and m. And a little bit more, or maybe a little bit less right skewed. A little bit more symmetry on this one. Change it again, say bump n to 20, keep m, well, bump that one up to 80. And it's starting to become symmetric. So for some values, it becomes more and more symmetric. For other values of the parameters for the degrees of freedom, it becomes more skewed. So that's our distribution. But the way we're going to work with this is we'll cite the F distribution inside of RStudio once we have a test statistic. Now, first, here's the idea of what we even mean when we say analyze the variances, or analysis of variance, or ANOVA for short. We're going to look into a ratio of MSG over MSE. So this will be mean squares for group, mean square for error. But let's carefully see how this tracks through, considering first our value k. So k is going to be the number of simple random samples you're going to have from k independent populations. So again, we're extending what we did in chapter 18, but now we have, say, 3 sample means, a mu1, mu2, mu3. We set them all equal to each other in the null hypothesis. So this is going to be our overall test, no difference between any of the means. After we do that, here's our two new quantities. We want to calculate to mean squares for group, mean squares for error, and those two components there are going to give us our f-test statistic. The idea is first, we take a value n. Sometimes this is called a total sample size. Sometimes it's called the grand sample size. I'll go with grand sample size. This is just your total sample coming from all populations. Add them all together, where k is the number of different independent random samples you have. Now we have a total sample size. And then we compute this object here, simply called x bar. This is sometimes referred to as the grand mean. What this is doing is just taking the mean of all individuals in the total sample, weighted by x bar 1, x bar 2, x bar k. These are the individual sample means coming from the k independent populations. So we have a grand mean, a grand sample size, and then putting that all together, when we say the f-test statistic has a m degrees of freedom numerator and degrees of freedom denominator, it comes from these values here and here. So these are what the degrees of freedom are going to be. Numerator degree of freedom. It's the number of groups minus 1, similar to chi-square for a one-way table, the goodness of fit test in chapter 1. This is going to be the denominator, degrees of freedom. And if we analyze what these are trying to say all together, we look into essentially, let me open up another tab just for a quick reference. All we're really looking into is types of variances. So we're going back to chapter 2 in a real sense. It's kind of interesting in a way. Here's how the ordinary variance is calculated. You compute a mean. For us, the mean we're looking into is, let me just move things over just a little bit more. There we go. So here we calculate a mean. And that's what this mean, the grand mean's role is playing in our current chapter, analysis of variance. Once you have the mean, you can calculate the variance itself. And we often just square rooted that, we got the standard deviation. But in analysis of variance, we're not worried about standard deviations anymore. We want variance specifically, s squared. All this is looking at the sum of the squared deviations of each individual in the sample from its mean. And in a real sense, that's what mean squared for groups is doing, MSG. The individuals are not individuals in the sample. The individuals here for this variance is all of the independent sample means themselves. So we measure k independent simple random samples. We take the sample means, x1 through xk. We wonder, how different are all those sample means? We calculate the literal variance of those things. K minus 1 is just the number of sample means minus 1. We take a sample mean. How different is it from the grand mean? That's the minus in terms of it being squared. And then just add them all together. They're weighted by the sample sizes. So if the samples are unequal, one mean doesn't have any huge influence. So we just call that variation among the means. That's the numerator of our test statistic. How much do the means vary? The denominator is how much variance is there in the entire sample. So if there is a lot of variation in the sample means, our test statistic is going to become large. We'll reject the null hypothesis that the means are all equal. But if the variation among the means is pretty close to the variation amongst the individuals in the sample, our test statistic is small and will fail to reject the null hypothesis. This one's a little bit different. If we were, say, back in chapter 18, and we assumed equality of variances, this is just the pooled sample variances for, say, 2 observations or 3 observations or off to k. So here, one big assumption with the ANOVA is in ANOVA, very unlike chapter 18, where we allowed for unequal variances. We made no comments one way, whether the variants are equal or not. But in ANOVA, we assume variances in each independent sample, of which there are k, are equal. And all this is doing is pooling the variances amongst all of the samples. Pooled variance. So it's weighted by the sample size minus 1, so that if the sample sizes are wildly unequal, one sample doesn't have more influence than the others. Then we take a variance squared. Excuse me, a variance is just the standard deviation squared. So we take a variance, it has to be S1 squared, multiply it by the next sample size minus 1, variance there, sum through and divide by the total sample size, or the grand sample size, minus the denominator degrees of freedom. So this is how we would have pulled the variance, even if we were in chapter 18 and we used that procedure. So these are the core ingredients for what ANOVA is at the moment. What we'll do for our first problem is just track this through by hand to see how it goes. For our second example, we'll show how to just throw it all into RStudio and do one fast analysis. But any questions at the moment, folks, with the statement of the definitions? Okay, well, here's the next level. Let me see if I can just zoom out for just temporarily, just for a touch. Here's what our null hypothesis is going to look like. Mu1 equals mu2 through mu k. Again, if we were back in chapter 18, it's really the same null hypothesis. You can add mu2 to the right, and H0 would be mu1 equals mu2. But if there are 3 or more means, we just keep on going, throw in another equality. Very similar to, say, chapter 21, our first chi-squared procedure. So our null hypothesis is that all the populations are different, that there's no difference whatsoever between the population means. But the alternative says there is some difference. At least one pair of these means are different. Mu I is not mu j for some index I not equal to j. When it says for some, just like with the chi-squared procedure, it could be exactly one equation. 2 means are different, or maybe 3 means, or every single one of these are completely different. We're doing another overall test. We're seeing if there is at least some difference, and then a follow-up test would have to be done, of which there's quite a few actually, to determine the nature of the distance. Simultaneous confidence intervals can be given, and so on. So all the F-test statistic is doing is saying, how much variation is there in the samples, that's MSG, divided by how much variation is there amongst the individuals, and if there's a lot of variation in the sample means, the F statistic is large, and that tells us that must have been a false statement. The means are too different, the variation is high. So we reject the null, and we'll make that conclusion there. But at least one pair of means is different. So that's the logic so far for what's going on. On the next level, when we go to calculate the p-value, we'll say p for probability, f because it's the F distribution. We take the numerator degrees of freedom, k minus 1, divide by the denominator degrees of freedom, n minus k. And just like for our chi-squared procedures, because it's an overall test, it's always that for the p-value. There's only one p-value formula for ANOVA, specifically this. It's a right-tail test every single time. Well, that's the full analysis, the entire write-up of the procedure. Our first job is look into what these formulas are saying even more closely by putting them to an example. Any questions at all, folks, before we take a look into the first example for ANOVA? Okay, once again, it's always good to compare what we've done before because the analogy here is extremely strong. When we were in chapter 18 and we did a hypothesis test, much like we're about to do here, We had very different conditions, the robustness conditions, but here's how we started off. We defined the parameters. You could have said mu1 equals mu2 if you wanted to. That would have been fine. Against mu1 is not equal to mu2. This time, we're going to write out this way for the null, that way for the alternative, and we'll just have more than two means as a guarantee. So that's really the only difference is starting this out. The other key difference is our condition checking is quite a bit different than chapter 18. We're assuming equal quality of variances, and so that's part of this right here, condition 3. The largest sample standard deviation is no more than twice as large as the smallest sample standard deviation. That's going to be our benchmark for robustness. If that's met, if the largest standard deviation is no bigger than twice the smallest one in our set of all standard deviations, then we consider this to be a reasonable assumption of our data that the variances are equal, and we have an accurate p-value that comes out using ANOVA. If this is violated, ANOVA doesn't work, we have to use non-parametric methods, of which there's a good set of methods that can be used. Other issue is, because it's a F-test statistic, it's really sensitive. If we have distributions that are skewed, the central limit theorem does not rescue us this time. Large sample sizes aren't going to help for skewed distributions. If there's outliers, it's just as bad. No central limit theorem here whatsoever. But in chapter 18, you could overcome that. If we looked at the conditions here, it said, in robustness conditions, if your total sample size is large enough, you can overcome the fact that some of the distributions could be skewed, that there could even be outliers, if you have a very, very large sample size. That falls apart here. ANOVA is very, very sensitive. There's no central limit theorem saying that you can overcome skew for large sample sizes. And condition 1, this is just making sure we match the procedure. We have to have k-independent simple random samples where k populations are being compared. And let's make one more statement. K must be greater than or equal to 3, or else we're using the chapter 18 method, not this one. So conditions are kind of fast to check. A little bit easier than actually chapter 18 was, where we had to look at the shapes of the distributions, consider the total sample size to see if the central limit theorem could help us out or not. Here, we have to really hit all three. So that's the full write-up of the procedure. All we're going to do now is practice it out in a couple problems. First one is going to be this scenario here. But before we jump in, any last questions or thoughts at all, folks, about the ANOVA information? Okay, well, our first example is a real study. I think our next one is as well. This one was a PhD thesis in Purdue University, kind of older data, 1983. It says here, human beta endorphin, HBE, we'll use that acronym, is a hormone secreted by the pituitary gland under conditions of stress. So this looks like it's probably a psychology problem as well as an exercise science problem as well. An exercise psychologist, so that's a new field, measured the resulting unstressed blood concentration of HBE, human beta endorphin, in 3 groups of men. We have 15 who had just entered a physical fitness program, so that's the first column here. 11 who had been jogging regularly for some time. They would have to define what they mean by for some time in the study. So that's column 2, joggers. And 10 sedentary people. Unequal sample sizes, unfortunately, it's better to have them balanced, but our procedure will work for unequal samples. So here's our 3 independent samples. The people who are just joining a fitness program, people who have been jogging for a while, so we assume relatively fit, and people whose fitness is a little bit more sketchy, sedentary group. We're told next, the HBE levels in, let me know if I read that unit wrong, I think that's picogram per milliliter, are shown in the following table. So the unit here is picogram per milliliter. So they measured the human beta endorphin levels for their unstressed blood concentration amongst 3 independent populations. So that's our study. Again, it almost looks like a chapter 18 problem. And if you just delete that column, the sedentary, or maybe delete this column, it could have been a chapter 18 problem. But they were looking to the 3 groups. So here we're using ANOVA. Well, thinking back into this table, one more thought about this problem is there is absolutely one quantitative variable. The quantitative variable is the HBE measurements in picograms per milliliter. And there is also one categorical variable. The categorical variable is the one that classifies everybody in this study according to which population did they come from amongst these different 3 here. So we hit both of those criteria. And that's why it's become a chapter 24 ANOVA problem. To start it out, we're doing almost exactly what we did in chapter 18. We begin by defining the parameters. Let's say let mu1, mu2, mu3 denote the population mean you could say human beta endorphin. I'll go with the abbreviation HBE in this particular unit. For, it looks like this was exclusively men, so let's just say here, for all men, that, and then just read out the 3 dependent populations according to these groups. So I'll say that are fitness, program entrance, joggers, sedentary, respectfully. So once again, saying respectively means mu1 has corresponded to the mean HBE levels for the fitness program entrance. mu2 corresponds to joggers, and likewise mu3 corresponds to the sedentary group. And there's no harm if you prefer to just write out 3 sentences. Let mu1 denote population mean HBE for fitness program entrance. Sentence 2 says, let mu2 denote the population mean HBE for joggers, and so on. That's always completely appropriate as well. So that's our parameters. Next thing we do is we're going to state both the null and alternative. This problem has no mention whatsoever of a significance level alpha, so we'll provide our own for this problem. Let's say let H0 be the statement that there is nothing going on in this problem, that the average HBE levels for all groups of men in this problem are the same. So that's the statement that mu1 equals mu2 equals mu3. Nothing is happening in the data. And that's what the null hypothesis is always all about. No effect happening. We'll test that against the statement that there is an effect going on amongst these populations, but it's going to be an overall test. So we'll say mu(i) not equal to mu(j) for some I not j. So this is an overall statement that really says a lot at once. It's saying mu1 is not equal to mu2, or mu1 is not equal to mu3, or again, mu2 is not equal to mu3, or yet again, mu1 is not equal to mu2 and mu2 is not equal to mu3. This is a gigantic compound statement, and you can write down those 4 outcomes if you prefer, but notice if there was 4 parameters, it's more than 4 outcomes. There's a lot of differences that could occur and might not occur. We're testing for any difference whatsoever. This is the so-called overall test for any difference in the data. we look at our means, the first two groups probably are not significantly different. The sedentary had a higher level of HBE. They might have been slightly more stressed. So we're going to see if that was significantly different amongst the other means. Well, any questions at the moment, folks, with our null and alternative? One thing I forgot to put down is alpha level. Let's say at alpha equals, let's go for, say, a 0.01. Next thing we are going to do is calculate the F-test statistic, but this is where it just turns into essentially a big math problem. So let's track this out. Purpose of doing this by hand is just to take another look once again. What is an analysis of variance all about by tracking through the specific formulas? So here's mean squared groups, mean square errors. What we need next is, well, maybe first, before we calculate either one of those, is the grand sample size. So n is going to be n1 plus n2 plus n3. We can see it on the table above here, but let me screenshot that down. I'm thinking we're going to need to have a good view of that as well. Okay, so here's the math part of the problem once again. Calculate the grand sample size. That's just going to be 15 plus 11 plus 10. So that's going to be 36 altogether. Next, what should we calculate? Probably for this formula, maybe the next easiest thing is going to be k minus 1. K is the number of groups, number of populations, independent populations in the study. From here, k is 3. That means k minus 1 is just 3 minus 1 for a value 2. So we've got the denominator. We know what n1 through n3 are going to be, but we still need the grand mean, x bar itself. So the next thing to calculate is x bar. This one had a formula that went n1, x bar 1 plus n2, x bar 2 plus n3, x bar 3, divide by the grand sample size n. So all this is doing here as a statistic is saying, if the null hypothesis is true, all the means are the same. We're pulling the means together. We're going to calculate a grand mean for the entire problem. So that's our first bigger calculator computation. Let's come down here. Take carefully. Actually, let me write it in on the document just so we can see what exactly are we calculating. N1 is 15 times the mean 38.7. Plus on the next level, N2 is 11, multiplied by the mean 35.7. Plus sample size 3 is 10 times the mean 42.5. Divide all of that by the grand mean n, which we found to be 36. So now coming back down over here, throwing all that in the calculator will be 15, 38.7, plus 11 times 35.7, plus 10 times 42.5. Divide by 36 observations, gives us that as the grand mean. I'll keep, say, how about 4 decimal places on this? Let me just double check my numbers. Okay, 38.8389. Hang on, 38.8389. Always good to double check on those values. Once we have that down, the next thing we want to take a look into is going to be, once I get my windows just where I want them, we can now calculate the mean square amongst groups. Here, what we're doing is we're looking into all 3 means here, and we're calculating a variation, a literal variation amongst 3 observations, those 3 means. The formula is directly imported from what we did in chapter 2. This is the strict variation formula. So we can now say mean squared due to groups. Variation amongst the three sample means is going to be, by formula that we see down below, take the sample size n1, 15, multiply it by the mean that we observed, 38.7 in that group, but subtract from that the grand mean. That was actually pretty close, 38.83, 89. We square that and we do it again. We go to the next sample size, 11, take the mean, 35.7. We want to know the difference between this mean and the grand mean squared, weighted by 11, the number of observations in that sample, 38.8389, squared, and then one more time, sample size 10, mean 42.5 minus 38.8389 squared. So these first two terms, the mean and the grand mean, are pretty close, but that one's quite a bit different. It's like when we looked into chi-squared components, if mean squared due to groups is large, the F's test statistic is going to be large. That's because of that one term right there. The sedentary group's mean was quite a bit different than the grand mean. So we divide all of that by k minus 1, which is the value 2. Then jam it into the calculator, mean squared due to groups. Here is the calculator side of all this. Let me get a window that's going to make sense for this as a calculator tool. That should do the job. So we want to start with the group, 15 times 38.7 minus 38.8389. Square that, add to it, 11 times 35.7 minus that same mean, square it. Then one more time, 10 times the next mean, 42.5 minus the grand mean, square that one, and then just divide by number of groups, divide minus 1, 2. So altogether, we have 121.3528. Okay, well, any questions or comments at all, folks, on half of our test statistics, mean squared due to groups? Okay, next, once we have the mean squared due to groups, the last thing we calculate is the pooled variance amongst all observations. The variation amongst the individuals in the sample is how our author likes to denote this. This one is mean square error, MSE. This one's a little bit faster to calculate as well. All we're going to do is reduce the sample size by 1. So the first group is going to be at sample size 14. Multiply that by the variance squared, or excuse me, the variance. S1 is squared is the variance. That always kind of throws me off, it seems like. So if that's the standard deviation, we take that, 16.1, square it, and now it's a variance. And then just keep on going down the line. The formula says, go to the next group, drop the sample size by 1, so now it's a 10. Convert that into a variance by squaring it, 13.4 squared. And then rinse and repeat. This sample size drops to a 9. The standard deviation is 12.8, but we want the variation, so we square it. And then finally, the whole thing is divided by the grand total n, which came out as a 36, minus the value k, where k was 3 altogether. So this is going to be 36 minus 3, or just 33 altogether. So we're nearly there. We can now throw this into the calculator. Just another computation and get 14 times 16.1 squared plus 10 times 13.4 squared plus 9 times 12.8 squared. Divide the whole thing by 33, and this is now the pooled variance, 209.0636. So notice already right away, the mean squared due to groups, the variation amongst the means in the sample is actually small compared to the variation amongst the individuals in the sample. What's that saying is these means are actually all close to each other. Doesn't look like we have statistical significance, but our goal is to get the F-test statistic to see just how close we were. We want a p-value to be extra sure. And so this is the last step of the process. Once we have all that information put down on paper, oh, hang on, we Control Z that. Once we have all that information down on paper, the last thing we have to say is F is MSG divided by MSE, which is going to be 121.3528 divided by 209.0636. Throwing that into the calculator is pretty rapid. We're going to get 121.3528 divided by 209.0636. And that's our test statistic, 0.5805. So the test statistic is, once again, quite small, but from here we can now get to the p-value and see just how close we were to statistical significance. Quite a process because the formulas were a little bit more than normal, but you know, if you could get through the degrees of freedom formula from all the way back in chapter 18, that one was pretty involved as well, this one here, then this is not too bad. We're just doing something different than that to there, in other words. Any last questions or thoughts at all, folks, getting the test statistic? Okay, finally, as far as the p-value goes, we have exactly everything we need here on paper. The p-value, and our syntax will go probability. Let's maybe write out this way to say what we're computing. P-value. Now this is the R syntax, probability with the F distribution, PF. Throw in your F test statistic, whatever it was, 0.5805. So this is F. Next, throw in the numerator's degrees of freedom. That's just going to be this 2 that we were color coding, same color coding that we've been using throughout the notes. So that's the value 2. Formula for that is just K minus 1. After that, throw in the denominator degrees of freedom. That's this value, but let's simplify it for sanity's sake. It's going to come in as a 33. Formula for that is just N, the grand sample size minus number of groups, K. And the final thing, just like with all the chi-squared methods we looked into, is set lower dot tail equals false. So that will give us our p-value in one shot. Let's write this out. Probability F distribution, 0.5805, 2, 3, lower dot tail is false. And this is what we get for our p-value. It's gigantic in this problem, 0.6122 upon rounding. That is way larger than any appropriate significance level alpha we would ever put down on paper. So we can say for this problem, this is definitely bigger than or equal to 0.01, which is equal to alpha, which means we'll fail to reject H naught in this problem. So that's our work so far. Last thing to do is just put down an overall conclusion. based off that p-value, whatever we said our null and alternative hypothesis were. So we're nearly done with this problem. Let's carry down what the parameters were, what the null was, what the alternative was. And notice we're interpreting this hypothesis in really the exact same way we've done every hypothesis test. Even if it's not significant, we still return back to this. All we're going to say this time is our study failed to find significant statistical evidence in favor of whatever your alternative hypothesis happened to be. So we already said we're going to fail to reject the null. So coming back down here, we're going to say in ordinary words, this study fails to provide significant statistical evidence that now, once we say that, we'll say, we can't say that mu I naught mu j for some I naught equal to j, because then we sound like a robot. We have to return to what were the parameters in the first place. And we'll say that we failed to find a difference amongst any of the population means for these groups. So return back to this definition, and we'll say we failed to find significant statistical evidence that the mean, or let's put it in the same wordage, the population, mean HBE, I'll drop the unit and just go to the next statement since we don't have a confidence interval. Mean HBE for all men among those that, let's mention the groups, are fitness program entrants or joggers or sedentary, and the statement is are different because this is always a not equals for this overall test. It's always a two-tailed test in that certain sense. So we'll say are different. And let me put in, because I forgot to mention, and this is at the 1% significance level. Although our p-value is gigantic, it's still good to mention what our benchmark for evidence was in this problem. So we failed to detect any difference of means whatsoever. In the next question, we will detect some difference amongst the means, and that means there's more you could do. You could go beyond the overall test and say, why did we reject? Which pairs of means are actually different? But this is what the problem would look like if it's non-significant. Well, we did, folks. That's the conclusion on this one here. Any last questions or comments on just tracking through the nuts and bolts, the mechanics of ANOVA or otherwise? Okay, well, we're nearly done with the notes, just one example to go through. And the next problem goes a little bit faster, but as usual, we're not going to rush through this one. This will be the problem that we're going to finish off when we come back next class on Monday. This will be the last question that we will finish off before we return into the overall review. But notice this one's different. This one gives us the raw data, but in a way that's good because it means you can just take all of this data, put it into RStudio, and crank out the f-test statistic and the p-value just like that, much like how we did the ANOVA procedure for two-way tables. So these data are actually easier to analyze because RStudio wants to work with raw data just like this. Let's analyze the context to get started. It says, a biologist wished to study the effects of ethanol. So when we say like a alcoholic drink is 5% alcohol, that's what we mean, the ethanol concentration, we want to know the effects on sleep time. And I can tell you from unfortunate experience, the effects aren't good. You're not going to sleep well. But this is what they did. A sample of 20 rats, matched for age and other characteristics, was selected. So these rats are all the same, probably laboratory rats produced by a specific company for these kinds of experiments. They were randomly assigned to receive an oral injection having a particular concentration. And these are the concentrations. There's 4 different groups. And this looks like it was an experimental design. The 20 rats were randomly assigned these different treatments. That alone says our data, the results, REM sleep times that we got, consists of having 4 simple random samples amongst the 4 different populations, these kinds of rats being given these different treatments. So this is a nice experimental design. We have true random data this time. It says, completely analyze these data using a 10% level of significance. 10% is kind of unusual, but I thought I'd throw 1 out there just to convey it's like a 90% confidence interval, kind of on the low end, here kind of on the high end for significance, but nothing inherently wrong about it. We'll give a complete analysis on this, and the first thing we have to answer is, what is the practical question? There is no question mark here, but this context implies a question. You might say something along the lines, what is the effect of ethanol concentration on sleep time in mice? And a good word here is on average, because that's what our conclusion is going to be all about. What's going to happen with the averages that we'll have in this problem? Once we have that down, our next step is, well, just to define the variables. There is a treatment for the control group. These rats were given no ethanol whatsoever. The next treatment was 1 gram per kilogram of the body mass of the rat itself. So that's the next ethanol concentration, going up to 2 grams. And then these rats were completely plastered, 4 grams per kilogram. And notice the REM is kind of interesting. It's absolutely just tanking as that ethanol concentration goes up. These data look significant, but we want to now say how significant. So let's go through the next process. We'll say let. And there are 4 groups. You could call them mu1, mu2 through mu4. I think for this problem, it makes a lot of sense to let the first group be mu0. The second group be mu1. Third group be mu2. And this is jarring, but if this one is at 4 kilograms per gram, let's let the fourth group be mu4. So the subscripts are hinting at the concentration. You don't have to do that. You could call them mu1 through mu4, not skipping 3. But I think for this particular problem, it makes sense to go that route. So let those be the means among. Let me step back. This will be, let those be the mean. We have to say mean of what? It will be REM sleep time. For all mice given 0 grams per kilogram, 1 gram per kilogram of the mouse's body weight, 2 grams per kilogram, 4 grams per kilogram, ethanol, concentration, respectively. So that's our setup so far. Then as far as the next steps will go, As far as staying in the null and alternative hypotheses, they always kind of go the same, which is nice in a way. We'll say, let H naught be the statement mu naught equals mu1 equals mu2 equals mu4 versus HA. One of these pairs is unequal at least, so we'll say mu I not equal to mu j for some I not equal to j. So some pair where I not equal to j just means you can't take mu1 not equal to mu1. That would just be a contradiction. So we say different indexes there. So at least one pair of means are unequal. And we're going to test at alpha equals 0.10, a 10% significance level out of nowhere, but let's run with that. That's what they said for the problem. So that's how we'll analyze the data. So what we need to do next is check the conditions, see how this is going to run. This is a little bit trickier because, it's kind of a different set of data. But once we get the data into RStudio, really, really fast to calculate the test statistic and then jump to the overall conclusion. So I'll try not to race through this with the remaining time that we have. When we come back on Monday's class, we're pretty much just going to see how we did this, look at the syntax again, and finalize the question. First thing we need to do, though, is if our data looks like that, import that data. So I have it on the Canvas course page. It's not the Canvas course page. Here it is. This is the example 2 problem. So let me resize here and get this pulled in. Let me just wipe out the environment first. We don't need any of that stuff at the moment. Now go to import data set. It might have been a while since we've dealt with this with quantitative data. Click from text base. Go to wherever your data is contained in. Mine is this file here. I had to make it this clunky file since I can't just say example 2 multiple times in Canvas because we have multiple example 2s of data. So I'm just going to rename this something. Anything that makes sense. You could call this, say, it's about REM sleep time, ethanol. How about rats? Because that's the subjects of this group or this study. So I'll just call this rats, lowercase. We have the ethanol, that's the categorical variable, the treatments. We have REM, that's a quantitative variable. Import that. This is just the data view. We often click away. Expand the data frame, and here's our data. Now, as far as condition checking goes, the first thing we want to talk about is our data random and are the groups independent? For an experimental design, it's nice that all these rats were as similar as possible. And that's what rats provided by, for these kind of companies that provide experimental units for rats, try to do, make them very similar. Because once we randomly assign them to the treatments, that gives us the simple random sample and 4 independent populations. So we could say here, just briefly, since this is an experimental design, and the rats, or these are mice, they said specifically, and the mice were randomly assigned to the treatments. That is a bit redundant. A bona fide experimental design will give random assignment to the treatments, but we're just saying here for randomization purposes, being a little redundant. This is a simple random. Hang on, let me change my wording. This results in 4 simple random samples among 4 independent populations. So that's our just fast write up of randomization. We absolutely have the independent populations, and they are qualified simple random samples due to the bona fide experimental design. Condition 2 is a check for skewness and outliers. But as far as skewness goes, look how small our sample sizes are. Every group has 5 observations altogether. That's actually the minimum number you need to make a box plot. So it's hard to assess skew here. The major thing we're going to really assess, because the samples are so small, is actually outliers. That's the big one for these data. If we had more observations, skewness would make a little bit more sense. They'd be easier to detect in box plots and in histograms, but it makes less sense for very, very small samples like these. So here's how we're going to do this. For the condition checking, now that we have the data imported, let's call this whole line of syntax condition checking. Instead of producing 4 histograms, which will look weird because the samples are so small, and because we want to also assess outliers, we're just going to go for a box plot. It's been a while, right? So hit box plot. The way we do the box plot for this is a little bit different. I want simultaneous box plots for rats. So we say rats first. We have to throw in the quantitative variable, which is REM. That's not the right box plot. That's all 20 rats at once. So we need to separate this out according to the categorical variable, ethanol. And the way that's done in R, for ANOVA as well, is that one symbol there, tilde. We're going to reuse that for the ANOVA method called AOV in RStudio. So you go tilde to separate out the REM quantitative data according to rats, ethanol groups. We're probably going to want some labels. So we'll say for the X label that this is going to be ethanol concentration. For the Y label, we'll say that that's going to be the REM sleep duration. Well, I'll just say REM sleep in minutes to keep the title from being too long. And that does the job. This is our visualization of the data as simultaneous box plots. So again, we really cannot assess skew here unless these were larger samples. If there was 20 observations here, we would have said skewed right. But every line, this whisker, that line, the median bar, these are all essentially just the data of the problem. Every observation gave us a line, so it's less informative. But what we do know is there are no outliers whatsoever on these data. So we're going to meet that one condition as far as outlines are concerned. So visualizing the data for part 2, we can say there are no outliers and no skew due to sample sizes being 5 in all groups. So this condition is met. And in fact, what about equal variance conditions? Well, the width of all these box plots is nearly identical. That tells us that the variation amongst all these groups is about the same. So even if we used our rule of thumb that the largest sample standard deviation is no larger than twice the minimum standard deviation, it's going to be an easy pass for these data. So we can make another statement, part 3. The sample, well, let's say it this way, the standard deviations may be assumed to be equal. So this means all the conditions are met. All we need to do is just run the procedure on these data. It takes a minute, but we're over time. Sorry about that. I didn't realize we were so far on time on this one. What we'll do when we come back on Monday is just write the last few lines for the analysis of variance procedure. We'll spit out a test statistic like the F we calculated here and a p-value, so it won't take too much time to put in the last finishing touches on this problem. Really, the new thing about this one is just doing the data import and showing how to visualize the data. So I'll share this syntax and we'll update it, build on it when we finish this one on Monday before turning to the review. But sorry for being just nearly a minute over so far. Any last questions or comments at all, folks, before we call it a day? Okay, well, have a great weekend, everyone. We'll be back to it on Monday, turning over to the review shortly. And on the weekend, I'll be working on updating this information here, posting the review guides and so on. But have a great weekend, folks.